So I'm not an algebraic geometer, and what that means is that I am not claiming to be an expert in this stuff. That's just passing down the very basic pieces of my knowledge. This is stuff that I'm like barely learning. And so that means that a lot of it I like copied directly from books and then like did a certain amount of digesting and attempted to present in a, you know, the most categorical. I tried to highlight the categorical aspects of what was going on as much as possible, but there's probably going to be tons of room to increase that. And so if you can stop me and point out whenever you think that there's going to be more room for category theory, then that'd be great. Or yeah. Besides that,
What if you want less category theory? Then you're not supposed to say anything.
I don't want less category theory, so that's not a problem. Okay, and I also don't usually give talks like this that are not about my own research. I guess like I know that a lot of other grad students and seminars and stuff do a lot of time, spend a lot of time like taking books, taking a section or a chapter of a book and then completely absorbing it and then giving a talk on it in the seminar, but like I haven't done a ton of that. So it was a little uncomfortable for me to write this to a certain degree, but hopefully it's not too bad. So this is what I'm going to assume that you know. So hopefully it's not too much. It's just like what's a topological space in a continuous map. From ring theory, it's just what's a ring and a homomorphism, and also what's an ideal and what's localization. So those are the things from ring theory. And then from category theory, hopefully this isn't too much. It's just adjunctions, abelian categories, and even not very much, just the vague notion that it has to do with the Hom sets being abelian groups. And then I'm going to point out the growth and deconstruction showing up probably a couple of times at least. So if you know that, then great. And if you don't, then I don't think you'll miss much. Okay, so this is not something that I intended for you to read. So this is part of me not giving talks like this normally, but it's just a bunch of stuff that I want to say. To algebraic geometry. So algebraic geometry studies the duality between algebra and geometry. And the way that one of the main ways that it does this is by saying that rings are dual in a certain way to a certain type of geometry called schemes. And I've recently been realizing that this stuff connects to my own research, and people doing that sometimes call it two algebraic geometry. And so in two algebraic geometry, instead of talking about rings, you talk about some categorified version of rings, which I like to call two rigs. I get that from John, and a lot of that work is trying to see how can we think about certain categories that arise naturally in algebraic geometry as themselves being like algebraic geometry. And this stuff looks really cool, but the only problem is that I don't know enough regular algebraic geometry to say anything about how these categories look like a categorified version of regular algebraic geometry. So that's like why I'm giving this talk, is to teach myself some algebraic geometry and figure out what's going on. And some names that are attached to this stuff is Brandenburg, Shrivastava, Johnson Freyd, and of course, Jacob Lurie. And so, yeah, like John was saying, I'm going to try to give two talks about this because I can't fit everything into one. And so today I'm going to just vaguely throw the word two algebraic geometry at you, which is what I'm doing right now. And then after that, I'm going to like become much more concrete and go through a ton of definitions that are in Hartshorne, and we'll try to get up to the definition of quasi-coherent sheaves. If it ends up being that you ask so many questions or something like that, or the discussion goes so long that I can't get there, then there's no problem with that, I think. Yeah, and then next time, there's this whole geometric side of this stuff that I won't talk about today at all, that hopefully I get to talk about next time, related to vector bundles. And then after that, I'll try to get into the actual connections between this stuff and my research. Okay, so that's just stuff I wanted to say before I actually started talking. So I'm starting all the way back at Presheaves just because I know there's people in here who I don't know exactly how much category theory they know or how much algebraic geometry they know. So I'm just starting at Presheaves. So a presheaf of C objects, where C is some category, on a topological space is a functor from Tx op to C. So what is Tx? It's the topology of X. So the collection of open sets, but considered as a category where the morphisms are the inclusions. So the objects are the open sets, and then you just talk about the inclusions. So what do you get?
Is Tx always a poset?
Tx is always a poset, yeah.
Okay.
So for example, C being abelian groups is going to be mostly what I'm talking about today. I'm also going to like upgrade abelian groups to rings, but that's mostly what I'm going to be talking about. And then if you have an open set U inside of your space, then F of U is an abelian group. And if you have two of these open sets, one is inside of the other, then the functorness gives a map from F of V to F of U. So it's important to notice that this is going backwards from the way that you might think this inclusion is going, but that's why I put op right here. And so we call this map restriction, and that'll make sense when I go to the examples on the next slide. And we write restriction like the way that you restrict a function. And functoriality, so saying that composition is preserved, says that if you have three of these lined up and you restrict, then you could have just restricted to the smallest thing and it would have been the same. Okay, so like I said, we're going to take, is there a question?
Is AB a topos?
No.
So it's not set to some
no
power?
Yeah, so normally I guess you say presheaf is going to be, you take a category, not C, you take some other category and you take contravariant functors into set or contravariant functors into a topos, and then the end result is always going to be a topos. But here we're taking presheaves of C objects. So presheaves where the data that you're assigning to this stuff is not just sets, but you add on extra structure to it. Yeah, I think this is like what people first come across when they look at presheaves, or when they try to think about sheaves. They usually have tons of structure on it because that's what people care about. But I think it was like Grothendieck's insistence that it's better to start thinking about just presheaves of sets first, and then you can think about the extra structure later. That's like sort of the key observation that gets you started to think about topos theory. Okay, so yeah, so C is abelian groups. We're talking about presheaves of abelian groups. Here's an example of an abelian group. For every open set in your space, you look at functions from your open set into R. And you can add these pointwise, and I wrote down that addition like this because that's just how I like to look at it. It seems less arbitrary than saying just add things. But that's really what I mean, is just you take two functions on the same set U, and you can add them pointwise. So that's an abelian group. And this is going to give you a presheaf of abelian groups. Here's another one. Instead of just functions, you can consider continuous functions, because R's got a topology, and so does U as a subspace of X. And so you can consider continuous functions, and you can add them, and they'll still be continuous, and so still is an abelian group. And restriction is the main thing that I was trying to point out in the last slide. If you take a function and you restrict it, to some subset, that's still going to be a function. If you take a continuous function and you restrict it to some subspace, that's still going to be a continuous function. And so that all works out. I guess I should have put counterexamples in here, or non-examples rather, but I didn't do that. But here's like sort of an example that's a bit different. So if you just take a random abelian group, and then we can make up a presheaf called the constant a-valued presheaf on X. So it just says every open set, you give it A as its output for this presheaf, and every restriction map, since it's going from A to A, and the only thing we know about A is that it's an abelian group, you just say it's the identity map on A. And so it's very boring, but that's sort of indicated by calling it constant. So this is sort of an odd one because it doesn't look like functions on a thing, but I usually think about functions when I'm thinking about sheaves and presheaves. Okay, so a morphism. So we always want a category of anything that we're talking about because we're category theorists. And to get a category of presheaves, you'd say it's a natural transformation because a presheaf is just a functor. Morphism between them is just going to be a natural transformation. And I'll just continue unless somebody wants me to spend more time on it. So now sheaf is going to be a special kind of presheaf that behaves even more geometrically than those random examples that I gave before. So presheaf of abelian groups, we're going to call it a sheaf if it satisfies these two conditions, which I called locality and gluing. So for locality, it says that if you have an open set and then you have a cover of that and you have one of the elements of this, so you can think of that as a function on U. So you have U and then a cover of U and a function on U. The natural thing that you'd expect is that if this function, you restrict it to every one of these covering pieces, and it always gives you 0, then the whole thing was 0 because you covered it with a bunch of stuff that said 0 all the time. So then altogether, it's going to say 0. And then gluing says that it feels very similar when you first read it, but it says that if you have U and then you have a cover of U, and then now we're going to assign data to all of the pieces of the cover first. You say if each piece of the cover has a function on it, so I'm going to keep thinking about them like functions. And you know that if you take two pieces of the cover and the two functions that you gave to them agree on the overlap, then you should be able to glue them together to get a function on the whole space that you're covering. So locality and gluing. And so we'll see exactly what happens with these things in a sec. Okay, so examples. So functions also works out to be a sheaf, satisfies locality and gluing. Continuous functions works out the same, but the constant one is going to be weird. So the constant a-valued presheaf is not a sheaf, and you can realize it this way. If you think about the empty set as a subset of your space, then there's two different ways that you can cover it. There's the cover that has no pieces in it, and then there's the cover that has one piece, which is the empty piece. So these are two different things. These are two different ways of covering it. And in particular, we're going to take the first one. So I point out both of them just to make sure that you realize that I'm not talking about the second one. But this first one, it's covering it with no pieces. So I'm covering it with no pieces. So it's vacuously true that if you take an element of A and restrict it to some subset, then you get 0 for every subset that's a part of your cover because there's nothing in there. And so locality just says that, well, okay, because it's 0 whenever you restrict anything, that means it has to be 0 altogether. And so that means that A is 0. But I didn't say anything about what A was. It was just an element of capital A. Yeah, so f of the empty set has to be 0. But we already said that f of the empty set was A because everything was supposed to go to A. So this is not working. So we're going to change f a little bit and say that f of u is going to be the 0 group when you stick in the empty set. And then it will be A any other time. And that should work out fine. But no, it doesn't. This is also going to fail. So we tweaked it a little bit, and it's going to get a little bit better, but now we have to continue tweaking, but let's see why. So let's say that you have U and V are 2 subsets, and they're not empty. And their intersection is empty. So these are 2 disjoint subspaces of X. And take 2 different elements of your group A, and think of little a as being assigned to U, and little b is assigned to V. So this is like a function on U and a function on V, except they're not really functions, they're just elements of the group. Okay, so what happens when you restrict A to the intersection of these 2 things? Well, you're restricting it to the empty set, therefore it must be 0. But what happens when you restrict B to the intersection? You're restricting it to the empty set, so it has to be 0. So gluing demands that there's a third thing, which is going to be in the union of, so we should be able to glue A and B is what you get from that, from the gluing axiom. So gluing is saying that there has to be a third thing, C, that is the result of gluing A and B together on U and V. So that if you restrict C to U, then you get A. And you restrict C to V, then you get B. But that's what A and B were. So they have to be the same as each other. And that's a contradiction. Okay, so basically, you have to be able to glue these 2 pieces together and get something that's also in the group, but it has to be equal to them. And so therefore, that doesn't work out. So it doesn't satisfy gluing. So how can we fix it? Yeah, we want to give something that's like A on U and B on V, but nothing in A can possibly do that. And so the right definition is that whenever you have U is the empty set, then you give a 0. Whenever U is connected, then you can just give the group A. And in general, you have to take a direct sum of A a bunch of times for however many connected pieces there are to your subspace. And there's like sort of an easier way to say this that's that sort of feels a little arbitrary, but this says that you can take the group A and make it a topological space in the discrete way. And then you consider continuous functions from U into A. And that'll give you the same thing as what I described above. And so this is what you actually call the constant sheaf on X. It's not constant, but it's like as close to constant as you can possibly get. Okay, so I think this gives a ton of, I think this example was the one that gave me a ton of intuition about sheaves, about how weird they can be, they're not always functions, and about how important locality is and the ability to glue things.
So any space is going to have a fundamental group.
Yeah.
Which spaces give abelian groups? And would it make sense to consider continuous functions between the spaces rather than directly to the groups?
Which spaces give abelian groups? I forget the answer to that. Sounds like a thing that I remember considering once, but what was the second part of your question?
Just that rather than considering continuous functions from your space U to a group, consider continuous functions from U to one of these spaces.
Oh. Well, how would you define, so I'm talking about a presheaf of abelian groups, and so you have to end up with being able to add the things that you
Yeah, I was just wondering why we would choose abelian groups over choosing a particular kind of space for study.
Yeah, I don't know. I think people do put spaces in there, just like for the purpose of like reading straight out of Hartshorne and trying to like get up to what the definition is. I think that Hartshorne says abelian groups, and so I'm going with that. But I think I definitely have heard about people talking about, especially like topological groups, in place of A that are not discrete. But I don't actually know.
Thanks.
I think John is talking, but I think he's
Sorry. Probably the most exciting examples for Hartshorne would be sheaves of rings, as you already mentioned, and then sheaves of abelian groups are also show up a lot where you study cohomology using, in a sheafy way, using sheaves of abelian groups. So I guess we could just say that like you could study sheaves of all sorts of things, but there's certain kinds of things that algebraic geometers really like for reasons that will only become clear if we get a bit more into algebraic geometry.
Okay, so Presheaves on other things might be interesting, but they're not algebraic geometry, so we're not thinking about them.
Basically something like that, I guess.
Okay. So let's see, I think I'll continue. Okay, so category of sheaves. So morphism of sheaves, there's a lot of words to say that it's nothing special. It's exactly a morphism of presheaves. And because of that, it's a full subcategory. All morphisms of presheaves, if they happen to be between sheaves, they are a morphism of sheaves. Okay, so we get an inclusion functor, sheaves into presheaves, and it has a left adjoint, and it's called plus. I should have also said that it's called sheafification. Hartshorne doesn't say that, but I think most people do. And you can take a presheaf and always generate the sheaf that looks as much like it as possible. And I won't describe sheafification at all because it would take a ton of time to describe the actual procedure of building the sheaf on a given presheaf. But there is this one example, which is I've told you what the constant presheaf is, and I've told you what the constant sheaf is. And if you sheafify the constant presheaf, you get the constant sheaf. So that also sort of clicked when I realized that this was how sheafification works on a weird example. You just take any random abelian group and say constant presheaf, and sheafify it, and it like produces in a very canonical way the thing that I was describing earlier.
So it seems like you ought to be able to sheafify any object of a topos that comes from category of presheaves. So for example, a graph is a presheaf.
Right.
Sense.
Right. But a graph, I think specifically is not on a space, and so I don't know what the result is there, except I do know that the adjoint functor theorem should give you an adjoint as often as you want when you're talking about topoi.
Yeah, so we're just right now, I think we're just talking about sheaves on topological spaces and presheaves on topological spaces, not the more general concept of presheaf that includes a graph as an example.
Okay.
And we could go down that road, but that's...
Yeah, I'm just trying to tie it to the stuff that I'm familiar with, so I was wondering what would happen.
Yeah,
but
yeah, the buzzword you'd need to know is Grothendieck topology. You can talk about presheaves on any category, but you can only talk about sheaves on a category if it has some extra structure called a Grothendieck topology.
Okay, thanks.
Yep.
Okay. So that's it for sheafification. I just think you can't define sheaf without saying sheafification, but I don't think it'll come up anymore in this talk. Okay, but something that will come up is the stalk of a of a sheaf or of a pre-sheaf. Here I give the definition. So if you have a point in your space, before I say the definition, I guess the intuition is that you're talking about a topological space and you're talking about assigning data to each open set, but the topological space like has points, and for some reason we're just ignoring them up until this point. And so what exactly is the data that a pre-sheaf or a sheaf does give to the points in the space? And that's what the stock is you try to infer. It is the right answer to like what can you infer about data on the points given this stuff that's just data on the open sets. And so the stock is the co-limit of all of these groups that you're assigning to all the open sets whenever you're talking about the open sets that specifically contain that point. So you take the point and you ask, what do I know about it? And so you say, I look at every single neighborhood of it, and those have maps of inclusion into each other. And so then they have maps of restriction on the groups that you're assigning to them. And so as you take the co-limit of that, it's sort of shrinking down around the point. But you never really get there. Maybe you do in some weird cases, but you're not supposed to think of it like that. You think of it as never really getting there, but constantly shrinking down to it. And the end result is an abelian group that you're assigning to a point. So that'll come up later. And just a super important theorem about them is that if you have a map between sheaves on a space, then that map is an isomorphism if and only if the map that it induces between the stalks is an isomorphism for every single point. So the information that your pre-sheaf, that your sheaves are giving to the points pretty much determine everything that you want to know about these maps. So sort of, I guess, seems like it's saying that you could have sort of gone back and forth between open sets and points freely, and you're not really losing anything. That's just my interpretation after reading it very little. Okay, and something else that's going to come up about sheaves in the future is direct and inverse image. So first, direct image. If you have a map of continuous spaces, F going from X to Y, and you have a sheaf on X, then you can turn it into a sheaf on Y by precomposing with the pre-image function. So continuous says that the pre-image of an open set is always open. And so another way of saying that is that it gives a function going in the opposite direction on the topologies. Maybe now's a good time to try drawing on the slide. So if I have X going to Y, this is F, then that turns into a thing that goes from TY to TX. And that's the pre-image function. Then if you have a sheaf on this, so I'll say like op everywhere. And this is a sheaf into abelian groups. Then you can just precompose with this and it turns into a sheaf on Y. And so that's what F lower star is called. And this gives a functor like this. So it takes a sheaf in X and it turns it into a sheaf in Y, and it does it functorially. They're all, oh no. Okay, so I have to stop annotating. Okay. So here's the inverse image. This one's slightly more complicated, but it says that if we have a sheaf on Y, then we can go backwards from what we did before by saying that we can turn it into a sheaf on X by assigning to U this limit. So you take So I'll annotate again. I'll use a different color. Okay, so we have X and we have Y. And then we have this point and we have its image over here, FP. And so now we're gonna talk about these subsets V that are around this point because we have a presheaf on Y, or yeah, we have a presheaf on Y and that's called G. But now we're gonna take G of V for all of the points around, for all of these subsets V around F of P. And this is what we're going to assign to U. Wait, sorry. This picture's a little wrong. Sorry, what we're going to do is we're saying here we have U. What did I do? No, I'm talking, sorry, I just like copied a picture from a completely different slide. This P doesn't even exist at all. Okay, sorry, that was completely screwed up. Okay, so we have U inside of here, and then we have F of U. It's kind of the same. We have F of U over here, and so what we're going to do is say the data that we're assigning to U is we're going to take all of the V's that are neighborhoods of this, the image of this set. We're going to take the limit of all those, and that'll give us an abelian group, and that's the data that we're assigning to this set. Okay. So oh no, I left the annotation. Clear. Okay. Sorry, this annotation thing is sort of annoying. Wish I had a better way of doing it. Okay, and this inverse image thing, we can turn it into restriction. If we have a subspace of X, which is U, and some sheaf on X, then we can restrict the sheaf to give a sheaf on the subspace. So that's not the same thing as the data that's being assigned to the subset by the sheaf. We're trying to make up a new sheaf that only is being defined on this subset, on the subspace. And you just use exactly the thing that I just described, but with the inclusion map of U into X. And important thing to notice is that the stalks are the same for both of these things. But we'll leave that alone. So now I'm inserting in a hard pause to force myself to pause and ask for questions. That's a picture of Grothendieck, by the way. He looks like he's waiting for someone to ask him a question.
So are direct image and inverse image adjoints?
I didn't read the thing that said that, but I know that there's a whole bunch of functors that are adjoint to each other, and I don't remember which ones are which. So maybe you already know the answer and you just wanted me to say it.
They're adjoints to each other, yeah.
Which
There's
one's
a,
left?
what?
Which one's left?
Let's see. I did all this for Presheaves in my class. And at that point I would have quickly told you. And so it works a little different for Sheaves, but
The one with the limit needs to be the right.
that's what I was going to say too, or more precisely, I was going to say that the direct one was the left one, yeah.
Okay.
Yep.
Okay, so I'll continue. So I put these pauses specifically between the things that I think are different sections, the things I'm thinking of as different sections of the talk. So next, I'm going to talk about, now that we're done with sheaves, I'm going to tell you about schemes. But first, here's the spectrum of a ring. So if you have a ring, then an ideal of it, which I assume that you already know what an ideal is, but an ideal is called prime if it's not the whole thing and if you were able to take two things in your ring and multiply and end up inside of this ideal, the only way that you could have done that is if one of those things was already in the ideal. The reason it's called prime is because you're supposed to be thinking about the prime numbers in the natural numbers. So the only way that you can multiply two integers and end up with an even number is if one of them was already even. The only way you can multiply two things and end up with a multiple of 7 is if one of them was already a multiple of 7. That's what it's trying to say here. And we're going to use that for this definition of the spectrum of a ring. I've also seen this called the prime spectrum, which I think is really cool because it's really emphasizing that primeness is what's being captured by this. So this is going to be a space that we're going to make up based on the ring, and it's going to be super important for the rest of the talk. So the points of this space, so like the underlying set of the space, is just the collection of all the prime ideals. So I guess if you were thinking about Z, then this would just be like the collection of prime numbers, basically. But being thought of as the generators for the ideals in Z. And we're going to give this a topology by saying that if you had an ideal, then you make up this set called V of I, and it's the collection of all the prime ideals that contain that ideal. So like for the ideal generated by 4 in Z is one that is going to be contained in the prime ideal generated by 2. Or I guess a better example would have been 6. The ideal generated by 6 is going to be contained in both the ideal generated by 2 and the ideal generated by 3. So that would be like what this set consists of. And so that's going to help us define this topology, where these VI are going to be the closed sets. And if you don't like thinking about closed sets when defining a topology, then you can think about these open sets. So here's dF, where F is some element of the ring. You take the ideal generated by that, and then you look at V of that, and you take the complement. Those are going to form a basis, an open basis for this topology. So if you like open sets, then that's the one that you want to think about. Okay, so here's a space that consists of all the primes in your ring, and it's going to be given a topology like this. And before I give you even more structure, I have to define what that structure is going to look like. So that's what this is going to be, a ringed space. So that's just going to be a topological space X, and then a sheaf of rings. So, and that's it. That's all of the data of a ring space. You have a space, and then a sheaf of rings on it, and then period. That's it. To get the category of these, the morphisms have this funny looking form where you can have two different spaces and a sheaf on each of them, and the maps between these two things are going to be a map of the topological spaces, and then a map of sheaves, but you want sheaves on the same space, and so then you're going to pull back the X1, the X sheaf, you're going to pull it back to Y, or direct image it to Y, and then now you can have a map of Y-based sheaves. So is anybody noticing something about this? I thought I heard a mic come unmuted.
I have a question.
Yeah.
What is the topology you just mentioned in the case of the integers?
In the case of the integers, so I was starting to describe it a little bit. I said that if you have, if you look at 6, for instance, then it's going to be contained in 2 and 3. And so so 6 is not an element of this space, right? Because it's only primes. But what it is it is a, that's a weird sentence. It specifies a subset of the space, right? So if I stick in 6 here to V, then this thing that I described spits out 2 and 3. And so the set is 2 and 3, but it's being specified by a number 6. But I think that, and that these are supposed to be the closed subsets.
I'm a little confused. Are you saying, so there's a closed subset, which you're calling 6, which
Yeah.
is the, yeah. And I thought you said it's contained in 2 and 3, but I think, I mean, I think you actually, well, as the ideal generated by 6 is contained in the ideals generated by 2 and 3.
Right.
But in this setup here, I think you want to say that that 6 is a closed set that contains the points 2 and 3. It gets,
yeah, I mean,
opt
right.
in that
So,
way.
yeah, so if you're talking about the ideals, then the containment is like backwards, but I'm saying that this closed set, because the space is just a collection of primes, and so this set, if you stick in the ideal generated by 6, then the set that this is, the subset of the primes that this is going to give you is the set 2, 3. And so that's going to be one of the closed sets. And
So one of the
So
open
is any
sets,
finite set of, oh, sorry, go ahead.
sorry, I was just going to say one of the open sets then is the complement of 2, 3, and all other primes, essentially, the ideals generated by all other primes.
mhm.
Is any finite set of primes then closed and any infinite set open?
I think any finite set is going to be closed because you take the product of that, and that's a number which should give you that set as this VI. You
I guess
said,
those are Clopen sets.
right. I don't know about the infinite one because I think you have to be careful about.
Yeah, I think you should say
Cofinite.
infinite, you should say cofinite. The
Right.
cofinite ones, the complements of finite ones, which are like really infinite, are be open.
So for example, if you index the primes, taking the union of the primes with even index, so 2, not 3, 5, not 7, 11, so on, that would be an infinite one that is not cofinite.
Right.
Yeah,
Is
so that would not be either open nor closed.
thanks.
Can I mention another example? I don't know if
Yeah.
we're going too slow. So the example that a lot of algebraic geometers like to mention is that if you take your ring to be the ring of polynomials in one variable, and let's like do polynomials with complex coefficients, because that's actually works out the most easy. So you can think of those as polynomial functions on the complex plane. I mean, that's what they are.
You said 2 variables?
One variable, yeah. Trying to keep it simple. You could do
You said complex plane, and I just heard plane. I thought.
Well, see, what normal people call the complex plane, algebraic geometers call the line. But anyway, just the complex numbers. Yeah. And so, well, you guys have studied, some of you have studied algebra much more recently than me. And so they may have asked you, they may have like made you know stuff like, what's a prime ideal in this ring here? So I don't know, if you know, go ahead and.
Irreducible monic, something else, adjective polynomial.
It's an irreducible monic polynomial. Do you know what the irreducible monic polynomials are? Part of why I'm using the complex numbers is it's supposed to make things easy because the complex numbers are algebraically complete. So
yeah, so it just corresponds to the complex numbers themselves. right?
Yeah,
I mean,
right. So every polynomial can be factored into polynomials that are linear if you're working over the complex numbers. And so if you think about it a while, you see that
Well, every monic polynomial can, right?
they can all be factored, but they,
You may have a complex coefficient that is not a term of the form x minus a.
right, yeah, there could be a complex coefficient in there. And so you wouldn't get a unique factorization if you let your, if you let yourself fiddle with that, like x minus 1 times x minus 2.
Did he just freeze for everyone else?
am I frozen?
No.
No. Okay, so I'm not frozen. John's frozen.
Yep.
Okay.
Maybe you should just go on the.
Ideals just correspond to complex numbers.
Oh, you just came back. Sorry, you froze for a little bit, John.
Okay, sorry, I'll say it again. So the prime ideals in that ring of polynomials just correspond to the complex numbers, because you get a prime ideal from it generated by anything of the form x minus a, where a is any complex number. So these points in spec A are just points in the complex plane. So this is supposed to be reassuring that we're back down to doing normal geometry. The points are just points.
I think there's one other one, right? There's the zero ideal.
Yeah, so I guess the zero ideal, the ideal containing only of 0, that's prime 2.
So maybe I should pause this for later when it comes up in an example that I'll do later. It's more relevant after I talk about schemes.
Yeah. So anyway, so that's a more geometrical example than this prime number example, but they're both good.
I like the prime one because it like immediately points out how you can start thinking about number theory in this context. The primes are baked into the definition of this geometric gizmo. I'll continue now if there's not a question from someone else.
Does C of X have the discrete topology
Not in the.
with this spectrum stuff?
No, I don't think so. Let's see, where does the topology even come in?
Because so like all the open sets are going to be like subsets of the complex numbers, right? And if you get all subsets, then it's discrete.
Are you talking about the
those are
complex
sets.
one?
Oh no, so I think she's saying that when you take C of X and then you take spec of that, and you're supposed to get C, but with this extra point that I'll stop talking about. And what is the topology that you end up with? I believe that you end up with the Zariski topology.
It's called the Zariski topology. So,
Yeah.
so that's just what it's called. But it's not the discrete topology, because we've seen that well, just like we saw with the prime numbers, the closed sets are just the finite sets. Because the prime ideals, the ideals are just coming from multiplying finitely many factors. So the open sets are sets that are co-finite again. Yeah, so it's not really the same as the discrete topology.
Okay, I see that.
Yeah.
Thanks.
Okay. So let's see, continue. So next thing I'll tell you about is an extra structure. Wait, no, I was already telling you about this. I defined a ringed space, the space with a bunch of rings on it, given by a sheaf. And then a morphism is going to be given by first a continuous map between the underlying spaces, and then second, we're going to have to turn this OX, this sheaf on X, and turn it into a sheaf on Y. And then after we've done that, we can say it's going to be a map of sheaves on Y.
He asked if anyone noticed anything about that. That
Yeah.
looks an awful lot like the Grothendieck construction.
Yes, precisely. So here's what I came up with for that. Here's this functor, which takes a space and spits out the category of Sheaves. Oh, this is not a very good description of it because this is just pre-Sheaves. Should have said like Sheaves, ring valued Sheaves on the given space. But if you replace that error, then pretty sure that this category ring spaces is going to be exactly the Grothendieck construction of.
So do you just need a plus on the square bracket there?
Yeah, I guess so. Is that the way that you notate the category of sheaf?
That's sheafification.
Yeah, that's sheafification, but that's
Oh, I see. That's for a single sheaf, not the whole
right.
thing of sheaves.
Right. That's another picture of Grothendieck, but that's probably easier to guess in this circumstance if you didn't already know about this picture of him. Okay, so that's the category of ring spaces. So the reason I defined this structure is because the spectrum of a ring is naturally going to have this structure. You can see it in the theorem that's right there, but let's define what this is first. So if you have a prime ideal in A, that's going to be one of the points in the spectrum. And so just a piece of notation, A sub P is what we're going to call the localization of the ring A at the ideal P. And so if you take an open set in the spectrum, we're going to define this ringed space structure on it. So we're going to define a sheaf of rings on it.
Remind me what localization is? Is that
formally
rational
inverting
functions?
all of the
Okay,
elements
yeah.
in it.
All right, thanks.
Yeah. So it's exactly localization of, well, never mind. So for an open set, we're going to define this sheaf to give you the ring that the set of elements of this ring is going to be functions that go from U into the disjoint union of all of these localizations for all of the points, which are prime ideals, which are contained in this open set. Okay, so now I'm going to draw another picture. This one deserves it. So here we have, this is going to be U, and then here's going to be our disjoint union of A sub P's. Here's going to be a specific point P, and here will be A sub P. And so we're talking about functions. So here's U, and then here's disjoint union A sub P. And so we're going to be talking about functions that go like this. And the first condition says that this point has to go to this component of the disjoint union. The second one, I found it super confusing. And when I looked at other sources, they describe this definition differently. And so I can't directly compare it. But let's just look at it together. Hopefully somebody can correct it, maybe John. So you have a point P. There is a neighborhood V of P, so let's call this V, contained in U, and there's elements A and F in A, such that for any Q, so you pick another point, and let's call this AQ, F is not in Q, yet S of Q, that means where this point goes, the point in here that it goes to, has to be A divided by F. So I'm super confused by that because you're taking F and you're saying it's not in Q, but I'm localizing in a way that I'm allowed to divide by it.
How can it be in Q?
Well, it's an element of the ring, right? F is an element of the ring, and Q is a prime ideal of the ring, and so it's a subset of the ring. So it can be an element or not an element.
Okay.
But what I'm confused by is like, how are you dividing by F if you specifically said that it's not in the thing you're localizing by?
I think you may have Okay, I think you may have mixed up localization at and localization away from, which are
Oh,
both things people do.
right.
If we localize at P, it means we allow ourselves to throw in inverses of everything and every prime ideal that's not P.
It's not. You're right. I completely ignored that. I knew that at some point. I knew that when I was taking this class, ring theory.
Yeah.
Thing.
And
Okay.
that's supposed to be a sort of geometrical idea that, like, the idea is that when you localize at a point in the complex plane, it means you only care on what's going on right there. So you're allowed by functions that aren't zero there. And so that means you're allowed to divide by all functions that are like have their zeros somewhere else. So that's like, yeah, so localizing at is the same as inverting, allowing yourself to throw in inverses of things that are in prime ideals that aren't that.
Right. Cool.
How are you associating this statement logically for all Q such that F is not in Q?
Yeah, so
Or-
I was also very confused by that. This is copied word from word out of the book, and like I'm having a lot of trouble parsing the logic right here. Like I don't know what F not belonging to Q is a part of. Is it a part of the conclusion or part of the premise? I don't know.
Yeah, I mean, there's got to be a really nice way of saying what this is.
It
and
wouldn't
why
make
it's-
sense to have and if F not in Q was not part of the conclusion.
So you think F not in Q should be part of the conclusion?
Yes.
Yeah, you're right. Because if it was part of the premise, then you'd say all these things and the conclusion. No, that doesn't make any sense. You're right. So this must be part of the conclusion.
Maybe there should be a there exist in front of F not in Q.
No, because you already said there exists F back here.
Right, so, okay, so I think what it's saying is that there exists some F such that S of Q is equal to A divided by some F.
Right.
And that F has to not be in Q. So it's like saying,
Yeah.
like, you take some thing away from your generator for your prime ideal, and then the thing you map it to has to be something divided by something else where that something else is not. So it's like saying it's like a rational polynomial or something, I think, in the analogy. That's my...
Right. Yeah, I think that's what it's supposed to
Yes.
correspond to.
Mhm.
So I think if I'm going to add stuff to this, I'll say, like, okay, there's a neighborhood V of P contained in U, and there's elements such that for each Q in V, F is not in Q, and this is true. So I think like an implications right here maybe fixes the logic.
I'm guessing that if you specialize enough, then what it's saying is that... Oh, I hear buzzing.
Am I buzzing or is, I don't know.
I don't hear you buzzing.
I muted
So I'm guessing
myself
that if you
and
specialize
continued.
it, if you specialize it in the right way, then it's saying like, it's like, okay, it's the sheaf where like you get sent to the set of rational functions on that set, and you can't divide by 0 on that set. So you have to choose the denominator to be something away from the point you're localizing at.
Yeah,
Away
you
from the
can't.
prime.
Yeah, you can't divide by a function which is 0 on the set that you're trying to define your new function on.
Yeah.
Right.
Yeah, this all sounds very good to me. So there's a very nice, lovely sheaf on the complex plane, which for any open set or even Zariski open set gives you the rational functions that don't blow up anywhere on that set. And I guess this is sort of supposed to be doing that. And there probably is some better way to word it. There probably is some more beautiful way to think about this stuff.
Right. I think there are definitely like more elegant ways to phrase this definition, but I'm trying to stick to Hartshorne as much as possible here. And I was like fixing things like reframing it as much as I could without changing things drastically. But if I wanted to use someone else's definition, it would look completely different. I think it would like throw off the flow of what I'm doing here.
Mm-hmm.
Okay.
I have a question.
Yeah.
So OA of view, there's the co-limit in the definition. Is that the disjoint union of the elements of ideals, or is that the sum of ideals?
So this is the disjoint union of them as sets.
Okay, thank you.
Yeah. So the way I'm thinking of it is like these APs are fibers of some fibration, and then it's a fibration over U, and then S was going to be a section. But we don't have that language yet, so.
But for this to be a ringed space, we're regarding this set of functions as a ring, right?
Yes.
Okay.
Yeah, that's a good point. I haven't talked about the ring structure at all yet. Okay, well, I don't have the ring structure here. I don't know why I didn't include it. I don't know how you're supposed to add these things exactly, but
probably just I mean, this is a sum of rings, which is a ring, and I think you probably just do it pointwise.
Yeah, okay, I see. I was thinking like, how do you add things that are coming from these different localizations? But you don't have to do that. You just have to add functions which take values in these rings in the same rings at the same points. You can have different values, but they're all in the same ring. This reminds me a lot of like dependent function types. Okay, so this question at the bottom, I think we thought about it a lot, so I'll continue. Okay, so here's a theorem. It says if you have a ring, then the stock of this sheaf that we were talking about just now at a particular point is going to be isomorphic to the local ring. Wait, local ring? I didn't talk about local rings yet, so sorry, this slide should be after this one. Okay, so here's a thing from ring theory that I always...
You could have said localization. I mean, you told us what AP was.
Yeah. Oh,
so,
yeah, I did say that. Okay.
So you could just temporarily just say that.
Yeah. So the localization ring, that's what I meant to say. AP. So yeah, the stocks of this sheaf that I was talking about are always these localizations. And for any element F and A, if you look at this open set, these are the basic opens in the topology, and you look at the data that O is assigning to that, I should have called this OA, it's going to be isomorphic to this localization, this other localization, which is localizing at the point, which is the same as, or away from the point. So it's the same as localizing away from the ideal generated by that point. Okay, so, I mean, maybe this theorem would have been better after this slide anyway, but a local ring, this is a definition that I forget like all the time. A local ring is a ring that has a unique maximal ideal. So Z is not local because all of these prime ideals are maximal. There's no other ideals that contain them except for the entire space or the entire ring. And local homomorphism is just a ring homomorphism that preserves the maximal ideal in this specific way, that the pre-image of the maximal ideal in the target is the maximal ideal in the source. So this feels sort of topology-y. So here's some examples. If you have a field, that's always local, and all ring homomorphisms between fields are local homomorphisms. And if you have a localization of some ring at a prime ideal, that's always local. So the theorem before that I was saying is saying that the Stalks are always local rings, and that the image of the opens under these things are always localizations, but not at prime ideals, I guess. And so we have an example of a ring space. This spec of a ring is always a ring space where the Stalks are always local rings. And so we're gonna like turn that into a definition. A ring space is locally ringed if for every point, the stalk of that sheaf is a local ring. And a morphism of locally ringed spaces is exactly a morphism of ring spaces. But for every point, you get this map, which I'll describe in a second, and you have to specify that this is going to be a local homomorphism. And we denote the category by locally ring spaces. So yeah, what is this induced map that we're demanding is a local homomorphism? Well, we had a homomorphism, or we had a morphism of ring spaces. And so in particular, that includes this F sharp, which goes from OY to the direct image of OX. And so if you look at a component of that, so we take a particular V in Y, open, then here it'll give this component. This is like the definition of F lower star. So it gives a map like this, but for all these V's, and I'm talking here about a point, so what can we do with that? You look at all of the V's that are neighborhoods of this point, that are neighborhoods of the image of this point. So this is the picture that I was drawing earlier that I actually wanted to draw right now. So let me see, where should I draw it? So if this space X, I have this other space Y, and I have a point P, and then I have a point F of P. And now I'm going to be looking at all of the V's that are neighborhoods of this point. And I'm going to take a co-limit over all of those. That's specifically, like if I'm not thinking about this stuff at all, then that's just exactly what the stalk of OY at FP is. That's the definition, is taking that co-limit. I think I said limit earlier, but that's because I wrote down limit the way that they did in Hartshorne, which is direct limit, which is co-limit. But I mean co-limit. And so we're taking the co-limit of these V's, which are neighborhoods of this point, and that's giving us the stalk. But we could also take the co-limit of the pre-image of those V's and look at their data on X given by OX. So I kept omitting OY in what I was saying just now. But we take their pre-image and then look at the data assigned to that by OX. We can also take a co-limit there. Since we have like two diagrams of the same shape and we're taking co-limits and we have a bunch of maps between them, then we get an induced map by universal property. But this isn't exactly the stalk at P yet, because this is only a subset technically of all the neighborhoods you could have of P. But it is a subset of them. And so if you think about taking a co-limit of fewer things, then that should include into the co-limit of the more things. And so there is a map by universal property into this bigger co-limit, which is this, which I didn't write as a co-limit, but is all neighborhoods of P look at the data associated to them. So that's what the induced map here is. It took me a long time to like get comfortable with that. I don't have a scheduled pause, but maybe I'll pause anyway. See if anybody has a question yet about ring spaces or locally ring spaces.
So it's like saying that the morphisms of these things are local, but only on the stalks.
Yeah. Locally ring space, the stalks are local rings. The maps induce these maps on stalks. And when you look at those have to be local homomorphisms. Working out exactly what the map on stalks is what's tricky here. First you say, oh, it's just colimit, but then no, because this isn't all of the neighborhoods of P. It's only some of them. So that's the trickiness.
And what was that last map again?
This one?
Yeah.
I didn't. So
it's not just the inclusion.
So it's given by universal property, but I didn't fully work out 100% of exactly what it is. But just my intuition is you have the same stuff, except here you have a lot fewer of them because you're only talking about some of the neighborhoods of P, these ones that are given by pre-images of neighborhoods of the FP. And so because it's basically the same diagram, but with fewer things, when you take the colimit, it's sort of like taking the disjoint union of 3 things and the disjoint union of 4 things. The disjoint union of the first 3 things is going to include in a very obvious way into the disjoint union of the 4 things. And so I'm just like, my intuition says that when you take that to more complicated diagrams of potentially infinite things, then it'll still work out that you're just taking a colimit of fewer things, so it'll include into the colimit of a bunch of stuff.
Okay, thanks.
Yeah, so that's not the best answer, but like that's just my intuitive understanding of what's going on. Okay.
So some error, some size.
So theorem. This is a locally ring space. This sheaf that I defined on spec of a ring. Moreover, if you have a homomorphism of rings from A to B, then it gives you a backwards homomorphism of locally ring spaces. I started putting spec B here, so sorry about the inconsistency, but it goes from B to A, so that's backwards. And then there's this last part, which is that if you have A and B, any morphism of locally ring spaces between their specs, their spectrums, is precisely induced by a homomorphism between the rings. So can someone guess a categorical way of saying this stuff? Packaging this all up into a few words?
A contravariant equivalent.
So I heard contravariant and I heard equivalence. I don't think equivalence is perfect. It's really close.
Adjunction.
So I'm just going to say full and faithful, because we don't know that all of the objects are being given by this functor. But given 2 objects that are given by the functor, every single map between them is going to be given by this functor. And so that's full and faithful. It's bijective on the Hom sets, and then who knows what it does on the objects. It's not being specified.
Are you going to give any teasers about the objects?
Wait, what do you mean?
Well, should I like not, should I? If
Well,
you're trying to
okay.
build suspense, if I say something, it will destroy the suspense. But I mean, if you're not trying to build suspense, I'll just say.
Okay, I'm building suspense.
Okay.
Okay.
So all I will say is that Joe is very right that you're not getting all the objects. Not all locally ringed spaces are coming from rings. And then other ones are incredibly important.
Okay.
We're going to talk about them, right?
Yeah, next is,
Eventually.
oh, yeah, sorry. This was a question, and I confirmed it with Tim Hosgood. He did confirm that spec is a full and faithful functor. I don't know why Hartshorne doesn't just say that, but it's basically there. Okay, I am going to talk about schemes now, so I hope that that's what you're talking about.
Yes.
Yes. Okay, so an affine scheme is just something that is spec of a ring. So it's a ring space, or a locally ring space, rather, that is in the essential image of this spec functor that I was talking about before. So you have locally ring spaces, and that's a ton of stuff. But then you can take rings, and you have a full and faithful functor into there. So if you only look at what you get from that functor, you can take a full subcategory on those, and that's exactly an affine scheme. That's just what we're defining an affine scheme to be. So yeah, I said it's the essential image and of this functor. Okay, but we can get rid of the word affine. We say it's a scheme if a locally ring space is a scheme if you take any point, there is some neighborhood of it that when you restrict the sheaf to that subspace, you get an affine scheme. So you'll get a functor of a sheaf of rings when you restrict. And if it happens to be one of these sheaf of rings that I called an affine scheme, meaning specifically it's isomorphic to some spectrum. Sorry, my sentence is going on too long. Locally, so a scheme is one of these locally ring spaces. You take a point, a neighborhood of that, you restrict the sheaf to that subspace, it'll be an affine scheme. Okay.
So instead of together with, you mean such that?
Together with. Oh, yeah. Why did I say together with? Might be an instance of copying from Hartshorne and something like that. Together with. Oh, no, wait. Such that the topological space U together with the restricted. So like this should be in
I'm sorry,
parentheses.
yeah, you're right, sorry.
Is an affine scheme. So we call it sh, that's the category. And it's a full subcategory of locally ring spaces also. Is this definition clear to everyone so far? An example will come next, but if you understand all the words here, then I'll move on. Okay, so here's a bunch of examples. If you take a field, then spec of K is, remember, that's the set of prime ideals. It's only going to be one, and so it has 1 point. And the sheaf that we were talking about earlier is just the constant sheaf on K, or the constant sheaf on the 1 point valued in K. So if K is a field, then we can define the affine line over K to be exactly spec of polynomials in one variable. And so this is like the notation for the affine line, but we put a little K subscript here and say that's like the affine line for the given field. So the zero ideal is not closed, is not a closed point in the topology that I was talking about earlier. But when you take its closure, you get the entire space. So this point in spec of Kx is called the generic point. So this is something that's super mysterious to me and is a little bit spooky if I try to actually implement a visualization in my head about a point that if you take the closure of it, you get the entire affine line. It feels vaguely similar to like a point at infinity, being like a 1-point compactification of the plane or something. But also somehow it's not just very far away, it's like present everywhere behind like every spot that you're at. So it's not a point way off in the distance, it's a point that's like secretly everywhere that you are, which is spooky. So for some reason that point is not closed. You take its closure, you get everything. But every other point is closed. And they're in bijection with the non-constant, that's the thing that's the other adjective I was trying to remember earlier. Non-constant monic irreducible polynomials. And if you get K algebraically closed, then these closed points are in bijection with K. So that's exactly what we were talking about earlier. And similar story plays out for higher dimensions. You take more variables and you get a higher dimensional affine space, and the closed points correspond to just taking the field and taking multiple copies of it. So it looks, when you look at the closed points, it looks like ordinary stuff, ordinary algebraic geometry, I guess. And so here's an example of a non-affine scheme.
Joe, I have a question.
Yeah.
So what is the structure sheaf for C of X?
What is the structure sheaf for C of X?
So like so we're talking about how every, right, so you get this functor which gives locally ring spaces.
Mm-hmm.
And if you apply that functor to C of X, then the space you get is like the complex numbers with that cofinite topology.
Mm-hmm.
And then the sheaf you get, I'm wondering what that is.
Where should I define it? Oh, I guess I defined it here. So let's see.
Yeah, you'd made a guess, Jade, about that, which sounded right. That is in this general case. and so you could apply your guess to this example. In fact, you almost sort of were talking about the example when you were making the guess.
Oh yeah, that's true.
So,
Right.
So you were saying something like it's going to be, so we're looking for this sheaf of rings. So for any Zariski open set, we want a ring. A Zariski open set of the complex numbers is going to be a cofinite set. And your guess was that the ring of guys on that cofinite set will be rational to blow up on that cofinite set.
Yeah, that makes sense.
right. So I think this
And
sheaf that you end up with is the one that you normally just call the coordinate ring sheaf, the sheaf of coordinate rings.
Mm-hmm.
I think I need to also say like regular morphism or something like that, but I don't remember this thing. But it has to do with rational functions as well, right?
yeah, you want to, the reason for this inverting stuff, this A over F business, is that you want to get rational functions into the game, even though you just started with polynomials. But you don't want to have rational functions that are blowing up on your open set. Or, well, this, yeah, you don't want to have, so O sub A of U is not supposed to have any rational functions that blow up at points of U. I think that's the idea.
Okay, yeah, that makes sense to me.
Cool. Yeah, going through this, I think I was sort of trying to avoid actual algebraic geometry as much as possible, and like stick to like the category theory and the definitions, and like all these examples are immediately getting you into actual algebraic geometry when you start thinking about them. But I was also hoping that people would ask about examples and we could talk about them like this. So this is great. I have no idea how much time we have left. Oh, we don't.
We're over.
Yeah, we're over time right now. Okay. So I gave examples of affine schemes. I was about to give examples of non-affine scheme. So what do you think, John? You're muted.
What do I think? I think you should probably stop
Okay.
to set a good example.
Yeah.
And no one will complain if you go on for extra days, but they may complain if you go on for extra minutes.
Okay.
So yeah. So you might as well just stop and pick up with some non-affine scheme.
Sure. Okay, this is good too because if I did get to the end of my talk today, I was not going to go next week because I have to prepare my talk for the MIT seminar for next week. But since I have a bunch of slides left over and it's the more heavy duty stuff, then maybe it'll take us longer and I can I can just prepare a tiny bit more for next week, and all the stuff I already have is going to take up a good chunk of time.
Yeah, that's fine. It's also fine if it doesn't go the whole amount of time. No one will complain about that either, I don't think. So yeah.
Right. So I guess I'll just show you what we're going to do next week is non-affine scheme, and then what are OX modules and what are quasi-coherent sheaves. And then that's what I've prepared so far. So we could also get into vector bundle stuff. So that's what I plan to do next week.
Yeah, that sounds great.
Cool.
Yeah, so this is like giving us a tiny taste of the pain of reading Hartshorne, but like really watered down version of that pain feeling, which is good. So
yeah. I've tried to read Hartshorne a million times and I never get very far because I start looking at chapter 1 and it's just so, I don't know.
Is this chapter 1?
No, this is chapter 2.
Okay.
Chapter 1 is I guess traditional algebraic geometry. And but now that I've told myself I was going to give a talk about all these structures, then I could just skim it really fast and get all the structures and definitions and grapple just with those and not with real examples, and skate by that way. That's all I really want anyway, because I want to get the category of quasi-coherent sheaves on a scheme, and sort of hopefully not have to think about algebraic geometry a ton when I'm actually using that, and just use tons of cool properties that actual geometers have already proven. Just use these categorical properties to give cool examples of two rigs and stuff like that.
Okay, sounds good. Hi, Chetan.
Hi, John. How are you?
Great. Okay, I guess let's call it. Oh, well, anyone who wants to leave can go. Maybe Chetan's starting to talk to me. I don't know.
Yeah, I've got to get going, but thanks a lot. Look forward to next week. Okay.
Yeah, thanks, Joe. You covered more stuff than I thought. I thought you were going to somehow completely eliminate all algebraic geometry and just somehow be doing a categorical version of it. But this is actual stuff like like the schemes and so on. So that's
Yeah.
good. And some examples. I was really shocked by that. Yeah, that's good. But it's pretty important to have some examples.
Maybe we could talk more about it next time, but or one thing that we could talk about would be like a nicer characterization of how we're arriving at this canonical like structure sheaf for spectrum, because that definition is weird. And the other thing I was wondering about was there's some nice analogy between schemes and manifolds, that manifolds are like glued together patches of real space, and affine schemes are patched together affine schemes.
Right.
And I think we discussed this at one point before, but I don't remember like what we concluded. I was wondering, there's some really nice fact that the category of manifolds is the Cauchy completion of the category of Euclidean space and subspaces of it. And yeah, I was wondering if the same thing might be true for schemes.
I don't know about the Cauchy completion thing. Maybe John does, but I was going to say also that that I did say I was going to get into like vector bundle stuff next time, and that is where you're taking the sheaf and thinking that as a bunch of separated data associated to all these things, and like gluing it together and turning it into a space that has like a bundle structure over the other space. John, do you know about that Cauchy completion for?
Yeah, I think that doesn't work for schemes. So the Cauchy completion thing comes from it's a fancy ass way of using the fact that every manifold can be thought of as a submanifold of Rn for some Rn. Which is a non-trivial theorem. So you use that theorem, and then you get, well, Cauchy completions is about splitting idempotents. So you find an idempotent map from Rn to itself, who's, I'm getting a little confused right now, but something like its fixed points are this submanifold. But that kind of thing, I really don't think it works for schemes. I think it's not, they're more rigid and you can't play this trick. I will say that Grothendieck and others, I guess, but came up with a different definition of scheme that's, I guess, equivalent to this one, that he liked better. And you can find some nice, where is it? You can find some nice discussion somewhere online about different algebraic geometers discussing like how they like to explain schemes these days. And they basically, all the sort of cool ones, like this way of doing it anymore. I mean, it's very important to know this way because it's super commonly used. But there's another way where you think of schemes as sheaves on a certain site. So you think of schemes themselves as sheaves on a certain category with the Grothendieck topology. So I'm mentioning that just because some of the niggly aspects of that one definition that we had the most trouble understanding, which was like how you get the structure sheaf for on the spectrum of a ring. This other approach doesn't get you into that, and there may be other ways in which it's good. It's more abstract. It's more abstract than this. So you pay a price in some other way, but so yeah, there's definitely stuff to say about like how you could try to do this stuff a little differently. I'll try to find that discussion. It was pretty nice. I can't remember if it was on Math Overflow or on somebody's blog or something like that. Okay, I think we should quit for now. Okay, see y'all.